Salam, peace be upon you. My name is Muhammad Laiq Sadiqi, the father of Holophase. Part 13, Calibration, Holophase Language Standard, HLS, and Standardization, Shared Reality. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We are near the summit of Book 10.2, Measurement Engineering. We have built eyes to see phi, learned to measure its flow, omega, k, and discovered its nuts, defects. But now, we face the most profound challenge of any measurement science. How do we know we're all seeing the same thing? How do we ensure that my phase meter in Tokyo and your phase meter in Toronto are reporting the same phi value for the same phenomenon? Today, we build the bridge between private observation and public truth. We establish the Holophase Language Standard, HLS. This is the skill of the metrologist. You are entering the Bureau of Standards. It is a quiet, meticulous place where reference artifacts are kept under controlled conditions, and where the protocols that bind all instruments to a single truth are forged. Your job is to define the universal reference frame for phi and to license the windows in which our measurements can be trusted. Scene: the two interferometers. Imagine two laboratories on opposite sides of the world. Each has a beautiful Mach-Zehnder interferometer, built by skilled engineers. Each lab receives an identical sample, a small, pristine glass slide with a known, nanofabricated step on its surface. Their task? Measure the phase shift caused by this step. Lab A runs their measurement. Their software unwraps the interferogram and reports: phase shift, 3.142 radians. Lab B does the same. They report: phase shift, 3.110 radians. A difference of 0.032 radians. Is this significant? Is Lab A's interferometer more accurate? Is there a hidden tilt in Lab B's setup? Or is the difference just within expected noise? Without a shared standard, this is a dead-end argument. They could argue forever about whose radian is correct. This is our core puzzle. How do we create an absolute instrument-invariant reference for phi so that all measurements everywhere can be translated into a common language and directly compared? The problem: the gauge of phase. Phase, phi, is inherently relative. It is always measured with respect to some reference. In Lab A's interferometer, phi is measured relative to the phase of the reference beam in their apparatus. A tiny, unnoticed temperature change in Lab A's optical breadboard could have stretched it microscopically, adding a constant offset to all their phase measurements. Their zero is not the same as Lab B's zero. This is a gauge freedom. It's like two thermometers using different definitions of 0 degrees. To compare them, you need to calibrate them against a shared fixed point, the melting point of ice, the triple point of water. We need a phase triple point. We need to define this physical situation corresponds to phi equals 0 in the Holophase Language Standard. Defining HLS, the universal reference states. The HLS is not a single number. It is a set of reference states and transformation rules. 1. The primary reference. A plane wave propagating in a vacuum at a specified frequency is defined to have a constant phase, which we can set to phi HLS equals 0. This is our phase vacuum. It's a theoretical ideal, but it anchors our definitions in fundamental physics. 2. Secondary artifacts. Since we can't ship a vacuum plane wave to every lab, we create physical calibration artifacts. These are objects whose phi structure is known with extreme precision from first principles or from certification by a primary standards lab. Phage gratings. A silicon wafer with perfectly regular, etched lines. It acts like a diffraction grating. The phase shift it imposes is calculable from its geometry and the wavelength of light. It produces a known periodic phi pattern. A sample with a grid of topological defects, vortices of known charge, +1, -1, at known coordinates. Their positions and charges are certified. Step height standards. Like our glass slide, but with a height traceable to the definition of the meter via atomic clocks and the speed of light. When Lab A measures the HLS phase grading, they get a raw instrument-specific phase map, phi inst xy. They also know what the map should be in HLS units, phi HLS xy. The difference between these two maps is their calibration transform, a function, often just a constant offset and maybe a tilt plane, that converts their instrument's numbers into the canonical language. So here is our first coherence criterion for the entire measurement community. The HLS standard is a coherence pact. It requires that all measurements be reducible to the same invariant relationships, stripping away instrument-specific phases. The invariant relationships are the key. The absolute value of phi at a point might be gauge-dependent, but the difference in phi between 2 points, or the winding number around the loop, or the frequency omega, these are physical invariants. HLS ensures that when we report these invariants, we all get the same numbers. The licensed window, the domain of trust. Now, a crucial, humble concept, the licensed window. No sensor, no theory is valid for all of reality. Your beautiful optical interferometer works for visible light, on scales from microns to meters, for phase shifts up to a few dozen cycles before unwrapping fails. It does not work for measuring the phase of gravitational waves, too small, or the phase field inside a neutron star, too dense, wrong physics. The licensed window is an explicit declaration of the regime where your instrument, calibrated with HLS, is validated. It has 3 axes. 1. Spatial scale window. From minimum resolvable feature, for example 1 micron, to maximum field of view, for example 10 millimeters. 2. Temporal scale window. From fastest detectable frequency, for example 1 kHz, to longest integration time, for example 1 hour. 3. Dynamic range window. From smallest detectable phase shift, for example 0.001 rad, to largest unambiguous phase shift, for example 100 pi rad. When you publish a result, you must state, this measurement was made within a licensed window of spatial scale, temporal scale, dynamic range, calibrated per HLS protocol v2.1. This is our safety rail. Any claim or experiment must state its licensed window. Extrapolating results or models outside this window is prohibited unless accompanied by a new calibration and validation campaign. This prevents hubris. It stops someone from measuring fluid vortices with an optical interferometer and then claiming their model also explains vortex formation in galactic clusters without demonstrating that HLS and phi closure even apply at that scale. The coherence budget for a civilization. Before a community can adopt HLS, it must invest in a coherence budget of staggering scale. This is the budget for building a shared reality. Metrological capital. This is the infrastructure of trust. It requires primary standards labs with equipment better than anyone else's, maintaining the chain of traceability. It requires robust, tamper-evident certification processes for calibration artifacts. Budget rule. The uncertainty of the primary standard must be an order of magnitude smaller than the desired measurement uncertainty across the community. 2. Protocol compliance capital. HLS only works if everyone follows the rules. This requires open, peer-reviewed protocols, automated calibration software, and a culture that punishes quick and dirty measurements that skip calibration. Budget rule. The cost in time effort of non-compliance must be higher than the cost of compliance. This is built through certification requirements 10.1.4 and peer review. 3. Communications capital. The calibration transforms and artifact certifications must be shared instantly and securely across the network, enabled by 10.5.4. A lab in the field should be able to download the latest HLS calibration for their sensor model and apply it in real time. If this budget is insufficient, if standards are corrupt, protocols are ignored, or data is siloed, HLS fails. The community fragments into incompatible measurement fiefdoms. We must earn this capital through rigorous collective institution building. Our coherence gate for the entire HLS enterprise is interlab reproducibility. We don't just trust that everyone is calibrating correctly. We test it. Regularly, labs participate in round-robin tests. A central authority sends a certified HLS artifact, like our phase mask, to a dozen labs. Each lab measures it, applies their HLS calibration, and reports their phi map. The pass-fail rule is clear. After calibration, all labs must report the same phi map for the artifact within their stated HLS-derived uncertainties. The variance across labs should be consistent with the combined uncertainties. If lab A reports phi equals 3.142 plus or minus 0.001 rad, and lab B reports 3.110 plus or minus 0.001 rad, they disagree by 32 standard deviations. That's a catastrophic failure. The HLS framework has broken down for those labs or that artifact. The dissonance indicator is systematic, irreproducible disagreements between labs using HLS on the same standard testbed. This indicates either a flaw in the HLS definition for that regime. For example, the artifact's behavior depends on something we didn't specify, like humidity, or, more profoundly, that the phenomenon is not fully described by phi within that window. The holophase model itself may be incomplete there. If coherence breaks, we stop. If coherence returns, we continue. If a round-robin test fails, we have a crisis. We contain it by suspending the licenses for the affected artifact or measurement window. Labs go into a diagnostic mode. We revert to a more basic, agreed-upon standard while we root out the cause. The licensed window for that type of measurement is temporarily revoked until the issue is resolved. The prediction spine, the fruits of standardization. If HLS works, it yields powerful, testable predictions. 1. Convergence of results. As HLS adoption increases, the variance in reported results for standardized phi measurement challenges, for example, reconstruct this grating, will decrease across labs. The scatter in interlab comparisons will shrink toward the fundamental limits set by each lab's SNR and resolution. 2. Portability of programs. A phi program written in HLS, for example, create a vortex lattice with spacing d, will produce equivalent physical outcomes when compiled and run on different HLS-calibrated foundries within each foundry's performance specs. The program's intent is separated from the quirks of the hardware. 3. Localization of error. Disagreements between a digital twin's prediction and an experiment will become quantifiable and attributable to specific localized model gaps, not to global calibration errors. We'll be able to say, the twin matches the HLS calibrated data, except in this region of high shear, where our model of nonlinearity is off by 5%. This accelerates scientific progress. Falsifiability, when shared reality fractures. Our falsifiability threads are existential for the entire Holophase project. If, after rigorous HLS calibration, two labs consistently obtain mutually exclusive results for a well-defined phenomenon, not just differing within error bars, but fundamentally contradicting each other. For example, one finds a defect with charge +1, the other finds no defect at that location in the same sample. Then, the HLS framework fails to provide a shared reality for that system. The paradigm is incomplete. It suggests there is no single objective phi field that both instruments are accessing. Perhaps observation is fundamentally context-dependent in a way HLS cannot capture. If no phenomena can be reliably reproduced across labs, even with HLS, if every experiment is a unique, irreproducible event, then the entire enterprise of phi science is not empirically grounded. It would mean the universe is not describable by stable, shareable patterns in a field like phi. This would be a defeat for the entire ontological framework from episode 8 onward. These are not mere technicalities. They are the experiments that tell us whether we live in a universe that can be understood together or only privately. The triunity of standardization. HLS respects triunity by standardizing all three echoes. Time echo standardization, defining a universal time base. What is zero time? HLS might define it via an atomic clock signal broadcast globally. This synchronizes omega measurements. A rhythm of 1 Hz in Lab A must mean the same duration as 1 Hz in Lab B. Space echo standardization, defining a universal coordinate grid. The HLS artifact provides this. The x equal to 0, y equal to 0 point on the phase grating is the same physical point for everyone. This aligns K measurements. Motion echo standardization. By standardizing time and space, we standardize velocity. The phase velocity calculated from HLS omega and HLS k is a universal quantity. Calibration is the process of aligning your instrument's private time, space, and motion gauges to these universal echoes. Lanterns across scales, the universal need for a standard. The need for a shared measurement language is the foundation of all collaborative technology. Near scale, the kilogram. For centuries, the kilogram was defined by a physical artifact, a platinum iridium cylinder in Paris. All scales were calibrated against copies of this IPK. This was a primitive HLS for mass. The modern SI system defines it in terms of fundamental constants, Planck's constant, making it universal and artifact-free, the ultimate HLS move. Middle scale, the GPS network. GPS is a real-time HLS for position and time. Each satellite broadcasts its position and the exact time from its atomic clock. Your receiver measures the phase delay of these radio signals. By calibrating against multiple satellites, the artifacts, it solves for its own position and time offset, aligning itself with the global spacetime HLS. Without this shared standard, navigation collapses. If we ever communicate with another civilization, establishing an HLS will be the first and hardest task. We might send a physical artifact, a plaque with scale markings, or a signal based on universal constants, the hydrogen line frequency, pulsar timings. This is our standard unit of time, derived from the hyperfine transition of hydrogen. All our messages will be timed against this. It's a coherence pact across the stars. In every case, collaboration and truth require a shared reference that cancels out local idiosyncrasies. The ethics of standardization, the fight against private reality. This is where engineering meets profound ethics. Standardization is a moral act. It is a commitment to public, verifiable truth. In a world without HLS, those with the most sophisticated or most persuasive instruments could define reality. They could say, our phase meter shows the effect is positive, while others see it as negative, and the debate would be settled by authority, not by appeal to a common standard. This is the path to technocratic tyranny. HLS, as a public open standard, is a democratizing force. It gives a well-equipped community lab the same authority as a prestigious university, provided they follow the same calibration protocol. It makes truth contestable in a fair arena. The safety rail of the licensed window is also an ethical guard against overreach. It forces humility. It says, we only claim knowledge within this domain. Beyond here, we acknowledge our ignorance. This counters the totalizing impulse of any paradigm. Power without coherence is self-destruction. And coherence across a civilization begins with a shared, humble standard for what is real. A measurement scene, the round-robin test. Let's visualize our roadmap's measurement scene. Scene, an interlab round-robin calibration test. A central standards agency mails out identical certified phase masks, silicon chips with a precise holographically etched pattern that should produce a known phi HLS XY map under specified illumination. What is measured? Each lab uses their own interferometer with their own laser, their own camera. They measure the raw interferogram, unwrap it to get phi inst XY, then apply their lab's stored HLS calibration transform, derived from previous calibration with the primary artifact. They submit the resulting phi HLS submitted XY map. The agency collects the maps. They overlay them. The maps are nearly identical. The difference, maps between labs show only random pixel-level noise, with the standard deviation consistent with the lab's reported uncertainties. All labs derive the same grating pitch, for example, 10.00 plus or minus 0.05 micrometers. All correctly identify any topological defects in the mask as having charge +1. Consensus is achieved. HLS is shown to be working. The maps are wildly different. One lab's map shows a pattern rotated by 5 degrees. Another's shows a different spatial frequency. A third reports a defect where others see none. The disagreement is an order of magnitude larger than the stated uncertainties. The reason could be manifold. Lab A skipped calibration. Lab B used the wrong laser wavelength. Lab C has a misaligned beam. Or, catastrophically, the mask's behavior depended on ambient pressure, which wasn't specified in the HLS protocol for this artifact, meaning the HLS definition was incomplete. Consensus is impossible, revealing a breakdown in the shared reality framework. The recognition skill, seeing the need for a standard. You know a field needs this skill when you hear phrases like, well, in our setup, or you have to account for the background drift in our system, or when two groups argue over results without a clear way to adjudicate whose instrument is right. The moment you want to compare your number to someone else's number and find yourself lost in a thicket of instrumental systematics, you are in the desperate need of an HLS. The need arises the instant collaboration begins. The digital twin, the universal reference simulator. Our twin now becomes the ultimate HLS reference. It can simulate the HLS artifacts under perfect conditions. More importantly, it can simulate your specific instrument measuring that artifact. You feed your instrument's physical parameters, laser wavelength, pixel size, known aberrations, into the twin. It tells you what phi inster you should get when measuring the HLS artifact. You compare this to what you actually get. The difference is your calibration transform. The twin bridges the gap between the ideal HLS world and your messy lab bench, enabling the future, the foundation for collaboration. This skill, calibration, HLS, and standardization, depends on all previous measurement skills, 10.1.1 to 10.2.3, and the concept of standardized testing, 10.1.4. It is the keystone that allows reliable digital twins, 10.2.5. A twin can only be digital if it has a definitive real-world reference to match against. HLS provides that reference. You calibrate your twin by making it reproduce HLS-calibrated data. Large-scale collaboration and networking, 10.5.4, 10.7.2. You cannot have a network or a collaborative society if every node speaks a private language. HLS is the common protocol, the TCP/IP of phi reality. It enables distributed sensing, consensus on physical facts, and ultimately, phi-based governance. This is the transition from personal craft to civilization-scale engineering. The workshop door now opens onto a city. Zenodo and the protocols of trust. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. The papers will contain the exact specifications of the HLS reference states, the mathematical formulation of the calibration transforms as gauge-fixing operations, and the detailed protocols for certifying artifacts and conducting round-robin tests. They will formalize the concept of the licensed window as a bounded parameter space. This is the concrete, actionable documentation that turns our philosophical shared reality into a working engineer's manual. Return to the phi. Let us zoom out. We have built the final, crucial layer of measurement, the social layer. We have created a system to ensure that when we each look at the one field, phi, we can agree on what we see. We have defined a common origin, common axes, and common units for the phase landscape. We remember, there is only one field. HLS is our collective agreement on how to set the dials on our instruments so that we all report from the same vantage point within that field. It is a triumph of coherence over idiosyncrasy. We have added a profound collective discipline, the declaration of licensed windows and submission to round-robin validation. We do not claim infinite knowledge. We claim precise, calibrated, shareable knowledge within a defined domain. This is the foundation of a coherent civilization. Not a civilization of solitary seers, but of coordinated observers building a common map of reality. Closing. So, picture yourself in the Bureau of Standards. In a vault, under controlled conditions, sits the primary HLS artifact. Perhaps a perfect phase grating, its geometry defined by counting silicon atoms. On the bench, your lab's interferometer is being adjusted. You measure the artifact. Your software compares the result to the canonical HLS map. It computes a calibration file. Offset minus 0.05 rad. Tilt 0.001 rads per millimeter. This file is saved, cryptographically signed. From this moment on, every measurement your instrument takes is automatically translated into HLS. Your private eye has been aligned with the public reference. You have just learned to sync your vision with the world. This is part 10.2.4, calibration, HLS, and standardization. Shared reality. It is the capstone of Book 10.2, Measurement Engineering, and the social contract of the Holophase age. In our next and final session of Book 10.2, we will bring all these skills together. We will learn to build digital twins, predictive software mirrors of physical systems, calibrated with HLS data, that let us simulate, predict, and safely test our designs before we touch reality. We will build the mirror world where our engineering dreams are first given form. Remember, one field, phi, with its infinite echoes in time, space, and motion. We can now not only see it individually, but measure it together. Our solitary perceptions have been forged into a shared lens. We are ready to look at the same world and see the same truth. Salam and peace be upon you.